Hold on a second, guys. Okay, today we are finishing up. Is it 5.5? Yeah, 5.5. The spherical coordinates part. I just realized my tablet's not plugged in. One second. Get 5.5. This is continued, but I'm gonna put spherical now. Spherical. Dot dot dot. But it does. It blows my mind. Okay, so let's just start by acknowledging yet again we are developing a version of integration. And please do your best to continue to acknowledge the common threads. So I don't want to do a recall this time. I've done a bunch of these. In one dimension, it's rectangles. In two dimensions, or three dimensions, in Euclidean coordinates, you get well, in two dimensions, you're integrating, you see rectangular prisms. There's this issue with density for three dimensions. Polar coordinates is a different shape. Cylindrical coordinates is a different shape. And now we've got spherical coordinates, and our little building blocks will yet again be a different shape. This is the hardest one in terms of visualizing. It's the hardest one in terms of what you have to remember to write. So let's go through it nice and slow. And I'll draw one parallel example. We'll do cylindrical just so you can reflect on the difference. So here's X, Y, and Z. And for a cylindrical, let's draw a cylinder. I don't know, my hand is so unsteady today, but there's my cylinder. So let's pick a different color. For any one fixed Z value, I've got polar coordinates. I go up to a different Z value, I see polar coordinates there. And let's put one more. So for any one Z value, we do polar coordinates, and this generates a family of parallel planes. Right, there's this plane here for that Z height. I've got polar coordinates there. There's this plane here for that Z height. I've got polar coordinates there. There's the standard Z equals 0 plane. On any one of those planes, we're introducing polar coordinates. So that's the picture for cylindrical. Okay. Spherical now is going to look like this. In my opinion, I think in a lot of people's opinions, it's not maybe not even an opinion. Spherical coordinates is the more natural three-dimensional analog of polar coordinates, or a more natural analog. It's going to look like this. We're going to have a sphere. And we've got coordinates on the sphere coming from these lines of latitude and longitude. So we're going to have to develop those coordinates. And then we have a radius, a different kind of radius. We call it rho. And it's just the distance to the origin in 3D. So this is a direction where we're advancing rho in this direction. Or you could be over here maybe. And we advance rho. This is a Greek letter rho in this direction. Or you could be down here. And you advance rho in this direction. So unlike the polar coordinate r is the distance to the z-axis, right? R is a radius in just two dimensions, the x and the y coordinates. So we can write this, r is equal to the square root of x squared plus y squared. Rho over here is going to be the square root of x squared plus y squared plus z squared. It's actually the distance to the origin. So that's the first kind of thing you want to understand is the rho coordinate. And then once you kind of buy that, which is probably the easiest one to buy, then you want to understand how we isolate the next two coordinates. So we need two, it's three dimensions, so we need three coordinates. So far we've got rho. It did it again. The way it does that, rho, comma. Okay, the next one is theta. It's exactly the same theta as we're already used to. So I'm going to show you one line for a fixed theta. That curve right there maybe corresponds to that choice of theta in the xy plane. If you fix theta in the xy plane, the standard way we think about it, you get a line of longitude for the sphere. Let's try to draw one more at a different angle. If instead we chose like this theta here, right? We slice out a different line of longitude. So let's get another picture going. So here, I've isolated a second coordinate, theta, and we'll just do another picture to work with the first picture. Let's just do those two coordinates. So let's say, for instance, here's y, here's z. You pick a choice of theta. Let's say you pick this theta right here. Well, there's lots of choices of rho, the distance to the origin. You can be close to the origin, or you can increase rho and go farther from the origin. Let's say the choice of rho you pick is that choice right there. You've got a choice of rho, and you've got a choice of theta. Where are all of the choices that could correspond to this rho and this theta? Well, I'm going to try to draw all of them right now. Something like that. Mm, quite like that. Something like that. So we could choose that point. It would have a certain rho and a certain theta and a certain something else. We could choose that point. We could choose this point. We could choose this point or this point. And all of the points we've just chosen have the same distance to the origin and the same angle in the XY plane. So how do they differ? What is it that distinguishes all of these points from one another? There's more than one way to measure this, but the way that we use, the standard way, is we measure the angle from the positive z-axis. So so the name of this next angle is phi. You put a circle and put a vertical line through it like that. And up here is phi equals 0. Maybe right here would be phi equals pi over 4. This one here is phi equals pi over 2. And then the farthest we can go is all the way down here is phi equals pi. Okay, so that's 3 coordinates. Rho, theta, phi, and these are spherical coordinates. Let's just play around a little bit before I start doing problems, or before we even develop integration. Let's just try to draw some sets in different colors. So what I'm going to try to do is I'm going to state some relationships. And then we'll see what they imply in our little space. Let's try, for instance, phi equals pi over, let's do pi over, let's try it, pi over 4. What are all of the points where phi equals pi over 4? Well, for every point that we choose, it must be the case that it makes a 45-degree angle to the positive z-axis. So let's try to find some such point. So here's a line in the z-y plane. That point right there looks like a 45 degree. That point right there, that looks like it's maybe 45 degrees. All of these guys, right? Well, these are all different choices of rho. That's fine. It doesn't say anything about rho. All of those different points make a 45-degree angle with the z-axis. Over here, all of these points might make a 45-degree angle with the z-axis. I don't want those lines in there. Also, over here in the xz plane, all those points, all these guys here, and even in the z negative y direction, maybe all along here. So there's a cone. A cone of points. If you pick any point on this cone, the angle to the z-axis will be 45 degrees, power of 4. How about let's make it bigger. Phi equals pi over 3. Well, that's the same as a 60-degree angle to the z-axis. So the cone is more open. Maybe like this, maybe like this, maybe like this, maybe like Come on. This. So that is a more opened up cone, right? Like a flower or something opening up. And now maybe it's clear phi equals pi over 2 is the xy plane. Kind of fully opened up. And then if you go beyond pi over 2, you start to close in the other direction. So we could throw in like a big one, like maybe close to pi. So like maybe 7 pi over 8. It's very close to pi. So it's like a very, whoops, narrow cone in the negative direction. And then maybe just to finish the picture, we'll throw one more in there. This line here, this negative z-axis, that's phi equals pi. Okay, you can really see it there. The cone opens up and then closes in the other direction as we choose various values of phi. Now, what if we chose to pair these sets? Let's do a purple maybe. Let's take like the phi equals 7 pi over 8, and we intersect it. Come on. We intersect that set with something like rho equals 3. So we want all the points where phi equals 7 pi over 8. That's all the points on that yellow cone. But also all the points where, we also want to restrict that cone to only those points for which the distance to the origin is 3. So let's say, for instance, that point right there has a distance of 3 to the origin. There's a whole circle of such points. All the points I just drew right there in purple have a distance of 3 to the origin. So that ring is the set of points where phi equals 7 pi over 8 and rho equals 3. We could try, for instance, to intersect with the green set. Let's try to intersect the set where rho equals 3. Well, now it's all the points that are on the green cone that are also a distance, that same distance, so maybe like right here to the origin. This is a much bigger circle. Let's try to do a dotted line here. The circle that I'm indicating here in purple, which is supposed to be on the green cone, is all the points that are a distance of 3 from the origin and which lie on the green cone. Throw one more in there. I could intersect the blue set with all the points where rho equals 3. And now again, same distance to the origin, but we've got to be on the blue cone. So maybe it's like right there. This is a smaller circle. Why is it smaller? It's smaller because the blue cone has a shallower, more acute angle with the z-axis. So all of these purple circles that I've drawn so far are restrictions to these various cones of what set? Well, what if we just tried to draw the set rho equals 3? What is that set? That's the set of all points, a distance of 3 from the origin. That's a sphere. Can you see the sphere? This is going to be super hard because this is we're just sketching here, but All of these circles that I've indicated so far lie on a common sphere. Can you see it? Here we go. There's no chance of me getting this right. I didn't draw it well enough. That's too bad. Hopefully you get the idea. There is a sphere. It is the sphere of points where the distance from the origin is 3. I hate this tablet sometimes. Okay, I think you guys get the idea. That sphere intersects any one of these cones, giving you a circle. And then, well, let's go back to my first drawing. Is that going to help? Let's go to, yeah, if you look at this theta here or that theta there, if I did one more restriction, let's do an easy restriction. We'll do theta equals 0. If you took any one of these sets and tried to intersect with one more condition, theta equals 0, or this one, theta equals 0, or this one, theta equals 0. Well, all of those have to be on the positive x-axis, right? That's what theta equals 0 corresponds to. We get a single point. There's the single point down there. There's the single point here. And then for the blue one, maybe it's like right there. Specifying all 3 of these guys, specifying a choice of phi and a choice of rho and a choice of theta collectively will give you 1 point. That's what it means to put coordinates on a space. That's what coordinates are for. That's what coordinates do. I really wish I could ask if there's any questions, but okay, you're gonna have to just go with whatever intuition you just got for it. But let's talk about integration now. So remember, if you have a function of any coordinates, but let's say we have a function expressed in rho, theta, and phi coordinates, and you want to integrate this with respect to the volume, first reflect what that means. You've got some shape, and just to have, let's put a shape in that will work with these coordinates. If you recall last time I was drawing like a top, let's do another one of those tops. So we have a cone on the bottom, and then I'll do a different color. We've got a sphere on the top, or something. That was actually terrible. Wow. Should be like this. That's a little bit better. Okay, I've got a spherical top and a conical bottom. And I want to integrate over this, x, y, z. Okay, so first things first, you always want to remember the function that you're integrating. If it's a 3-dimensional integral, it is natural to think of this function as a heat or a density so that you can grasp what it, from a visual perspective, what it is you're calculating. So to represent that, you can throw a bunch of dots in here. And eventually, when you do this, you want to, for representation's sake, make the dots denser in some places and less dense in others to indicate that maybe it's hotter in some parts or it's heavier, more dense. Just for the sake of visualization. Now you want to integrate. Always with integration, you are cutting your space up into many small pieces. And then each one of those pieces, you are estimating that volume, multiplying by the right density, adding everything together. Now let's see if we can pull this off. What would it look like in spherical coordinates? So here's some bit of coordinates in spherical. Let's go a little far. Let's go off the cone for a moment. What would it look like if we moved a little bit in the rho direction? So we have a little delta rho. We also moved a little bit in the theta direction. So we've got a little delta theta. And one more, we also move a little bit in the phi direction. So we've also got a little bit delta phi. Hopefully you can see the shape I'm indicating. I'm trying my best to draw it nice and clean. We need to approximate the volume of that shape. Well, that little bit of volume is roughly equal to what? We want the lengths of the sides. So delta rho is the length of that little bit of side there. The arc length coming from the delta theta, we've seen this before. Well, or hold on a second. Let me pause on that one. That's the one we want to really look at. First, I want to look at delta phi. So here's the little change in delta phi right here. We could also, I'm going to put more tick marks all up the line. All of the tick marks I've just put are the same size in delta phi, and they're the same change in length. Those lengths are all equal to delta phi times the distance to the origin, rho. We've used this already in spherical coordinates, polar coordinates and cylindrical. But there's something that happens, and what I'm about to say next, this is the hard part in terms of understanding this, and it's the following. Here is the change in length due to this variation in theta. And as I go up, hopefully this is going to become clear, it gets smaller. Why does that happen? Can you guys see that? All of those little magenta lines corresponds to the same delta theta. But they're not all the same length. They shrink as we go up. Take a moment and reflect on why that's true. See if you can explain it. Here's the deal. The arc length for phi is coming from, I'm going to draw this and then erase it, is coming from these tick marks all being the same distance from the origin. You guys see that? But the magenta lines all are all arc lengths corresponding to distances to the z-axis. And those distances are getting smaller. Down here, you've got this nice healthy distance, or down here, you've got the full length rho. And so that delta theta corresponds to this large change in length over here. On the other hand, by the time we're all the way at the top of our, little sector, a little gold sector here, you know, the this little length is much smaller. I'm going to say shorter. And therefore, that change in theta corresponds to a smaller arc length. And so what we need to know is, what are these magenta lengths? I'm going to draw it over here. Whoops. Here are all those magenta lengths. If you pick one of them, there is a distance to the origins right here, and we call that length rho. But the length that we're seeing appear here, in terms of this angle, this is phi here, is not rho. What is it? Opposite sine. That length there is rho sine phi. So let's go down here and keep our story going. Let's go with gold again. The arc length coming from the phi change is rho delta phi. But the arc length coming from the change in theta is that blue radius, rho sine phi. That's the radius for delta theta. And when we put it all together, we get rho squared sine phi delta r delta phi delta theta. Any order, doesn't really matter. That's the hardest part right there. You've heard me say this word in previous lectures, the Jacobian. You don't have to learn this word right now if you don't want to, but for polar coordinates, the Jacobian was r. The thing we had to multiply by to get the volume right was r. In cylindrical coordinates, it was also r. Now, it's not r. It's rho squared sine phi, which is just a more nasty term. So when we try to set up a triple integral in spherical coordinates, we're going to again do a sum from I equals 1 to n, another sum, I equals 1 to n, but j equals 1 to n, j equals 1 to n, and one more, k equals 1 to n. We're going to sample points, a rho I, a theta j, a phi k, and then we're also going to have to remember to multiply in this rho I squared sine of phi k, and then delta r, or delta rho, sorry, delta rho, delta theta, delta phi. And if we put a limit on this, as n goes to infinity, this becomes a triple integral. Bounds, there's going to be bounds here on everything, but we're going to be integrating not rho theta phi, but rho theta phi times rho squared sine phi. D rho, d theta, d phi. Boom. That's really the lesson for today. The rest is going to be examples, concrete examples. All we wanted to grasp that's new, that's theoretical in a new setting, is this new Jacobian, rho squared sine phi. When you integrate in spherical coordinates, you must always multiply by an extra factor of rho squared sine phi. Okay, let's just try to do some examples and see where we get. Um, let's go ahead and do this. Example. Here, no, it's too easy. Let's do this one. So they ask us to set up. So remember, for these harder problems, it's challenging enough just to set them up. We don't usually need to go through the calculations after that. We kind of trust that you can do that. So they say find the volume of, let's call this region E. And this region is given by, I'll say below by Z equals root 3 x squared plus y squared, and above by Z equals root 4 minus x squared minus y squared. So that's a top, like one of these conical tops, like the one I just drew. The top is a sphere. Whoops. Right there. Of radius, so if I square both sides, I get rho squared equals 4. Right? You bring the x squared and the y squared along with the z squared, you get rho squared equals 4. Or rho, the radius from distance from the origin is 2. The bottom is a cone. Well, first we can write it as z equals root 3r if you want. It's a cone with slope root 3. So if this is root 3, this is 1. That angle there is what? What is that angle right there? Pi over 3. Therefore, that angle there, which is phi, is pi over 6. So it's also, it's a cone, phi equals pi over 6. We try to sketch this. We have that pi over 6 angle. Cone. And the top there is rho equals 2. So here's what I'm going to do. I'm going to take theta from 0 to 2 pi. That's d theta on the outside. I don't care about theta. All theta directions work, right? Once I have picked a choice of theta, so here's one choice of theta. What do I want rho to do? I want rho to start at 0 and go as far as pi over 6. Let's throw that in. 0, pi over 6. That's d phi, not rho, phi. Now, for any one theta and any one rho, I keep doing any one theta and any one phi, I want rho to go from 0 all the way to 3. Hopefully you can see that there. Not to all the way to 2, sorry. Rho equals 2. So we'll have rho go from 0 to 2. That's d rho. And what am I going to integrate? Well, to get the volume, we always integrate the function 1. That will recover the volume. And I never forget, if I'm integrating in spherical coordinates, to throw in that factor of rho squared sine phi. So 0 to 2 pi, 0 to pi over 6, 0 to 2, rho squared sine phi, d rho d phi d theta will give you the volume of that top. We'll do one more example. Here they ask us to convert to spherical. So they give us an integral fully written out, and they say, turn this into a spherical integral. It's expressed as a cylindrical one, or not a, sorry, rectangular one. So here's what they give us: -1 to 1, 0 to root 1 minus y squared, x squared plus y squared, all the way up to root x squared plus y squared. They want us to integrate the function x, y, z, and the order here is dz, dx, dy. So that's an integral. It is expressed in xyz Euclidean rectangular coordinates. And they want it to be re-expressed in spherical coordinates. Now, as I've said a few times, I think in these lecture videos, you must conceive of the shape geometrically. If you can hope, if you want to hope, just to do these problems correctly. Okay, the first thing they give me is y going from -1 to 1. So this orange line here is y going from -1 to 1. That's the outermost integral. Then I've got x. X has to start at 0. That's this orange line that I've just drawn. This is x equals 0. And then x has to go as high as Root 1 minus y squared, that's a circle in the xy plane with a radius of 1. So here's that circle there. So that's what I see in the xy plane. And then z, what's the floor for z? X squared plus y squared. That's a paraboloid. It looks like this. I'll draw on this side. It goes up to there. And on this side, up to there. And then it's constant around the edge of the circle. That's the bottom. What's the top? The top is right here. It's a cone at a 45-degree angle. So here's the top now. This is a cone I'm drawing. So we have to go, Z has to go as low as the blue paraboloid and as high as the green cone. Blue paraboloid, green cone, blue paraboloid, green cone, blue paraboloid, green cone. So these lines here are indicating the movement of Z from the bottom paraboloid up to the top cone. With this picture fleshed out, we can now attempt to convert to spherical coordinates. I'll start by seeing that the largest theta value is pi over 2, and the smallest theta value is negative pi over 2. Right? It's all these guys here, all these theta values over here. So let's start with that. Theta goes from 0, no, not 0, sorry, negative pi over 2 to pi over 2. That's d theta. The next up, this is the hardest one probably for this problem. What are the bounds on phi? Well, the largest phi that we see is this 45 degrees here. Or actually, sorry, the smallest phi we see. Pi over 4. And then we need to go down from pi over 4 all the way to here. And that's phi equals pi over 2. Those are the phi values that count. Let's go throw that in there. Pi over 4 to pi over 2. That's d phi. What about rho? The bounds on rho are not constant. They depend on phi. You can see them here. We have to go as far as that blue line, which gets smaller as phi goes down. So that blue line is z equals x squared plus y squared. Z equals R squared. Um, Forgetting something. Okay, so I was trying to avoid doing this the hard way, but let's do this. So how do we actually find X, Y, and Z coordinates from spherical coordinates? Well, um, Z is equal to rho, the radius, times the cosine of phi. Why is that? If this is rho here, and this angle here is phi, then the height, the Z coordinate, is the hypotenuse times the cosine. So rho cosine phi. The radius in the XY plane is this other length right here. That's rho sine phi, and that's equal to R. And if you know R, well, X is R cosine theta. So rho sine phi cosine theta. And then Y is R sine theta. So rho sine phi sine theta. So with these equations, let's see what we can do. So Z is rho cosine phi, and R squared is rho squared sine squared phi. So I can solve for rho. I can, by rho equals cosine phi divided by sine phi squared, which is ugly, but it must be what they want to see. So you can rewrite that a couple different ways. That's the cotangent of phi times 1 over the sine is the cosecant of phi. So if rho goes from 0 to the cotangent of phi, cosecant of phi, that's the right bounds on rho. I'll put in d rho. I need more space. Just try to move that there. My integrand was x, y, z. I've got x, y, and z all over here. So x times y times z is rho cubed. Here's z, here's x, here's y. What else do I have? Sine squared phi. That's from this sine and this sine. Times cosine phi. I need more space. I also have a cosine of theta and a sine of theta. And then I need that Jacobian factor, rho squared sine phi. How will I get that? Well, I'll change that 3 to a 5. That's rho squared I just put in. And I need sine of phi. I've already got 2 factors of that, so now I got 3 factors of that. Boom. Rho to the 5th sine cubed, cosine phi, the sine, cosine theta, sine theta. Yeah, I knew I did something wrong here. So just so you know, let me just say real quick, that nothing that I just did is incorrect, but the problem does ask us to convert to cylindrical coordinates. I knew it because this paraboloid here is just not a natural shape to do spherical coordinates in. So this is everything I just did is correct. It's a good example. It's just way too hard. But let me just review what I just did for everybody's sake. So converting to spherical, it required expressing that paraboloid there as rho being a function of phi. So this is what we just did over here. It's fine, it's correct, but it's obviously super difficult. The idea is you wouldn't want to do a region like that in spherical coordinates. And polar, it wouldn't have been very hard because we would have just integrated z from r squared to r. So forgive me for doing an exceedingly complicated example, but it's good then if you follow along because you're not going to get anything this difficult in any of the problems you have to work on. Okay, I'm going to end the video here. As always, if you've got questions, let me know. Please try to keep up with everything, and I'll see you at my office hours if you want to. And also keep in mind, there is one more quiz, and then there is the final. So as far as exams go, that's all there is. Thanks, guys.